Hi friends, welcome to our channel. In this video, we are going to discuss about the Gilbert multiplier cell. Before going for this, we need to analyze why we are going for this Gilbert multiplier cell. If you see the emitter coupled transistor pair, it has mainly two drawbacks. That is, the input voltage V2 is offset by VB on, so the desired input V2 cannot be multiplied with any other input V1. And the second one is the V2 must be always positive, resulting in two-quadrant multiplication. To overcome these drawbacks, we are going for the Gilbert multiplier cell. In this Gilbert multiplier cell is also known as four-quadrant multiplier cell. It allows two inputs V1 and V2 voltages to swing in both the polarities. This method is the extension of emitter coupled transistor pair. In this circuit, it consists of three different stages with each stage having a pair of transistors. All these stages are emitter coupled transistor pair with cross coupled stage 1 and stage 2 in series with stage 3. The analysis of this circuit can be done using two methods. Analysis 1 using hyperbolic tangent function and analysis 2 uses the basic principles of transconductance dependence. First we are going to discuss the analysis 1. In this analysis 1, we need to know about the basic relationship between IE, IC and your input voltage. See, if you see the collector current of transistor Q1, so transistor Q1, this is the collector current IC1, emitter current is IC5. So by using this formula, general formula, IC can be written as IE divided by 1 plus e to the power of minus VI. V is the input voltage by VT. IE is nothing but emitter current. So by considering Q1, the emitter current value is IC5. So by writing the IC1 equation, IC1 can be written as IC5 divided by 1 plus e to the power of minus input voltage. This Q1 is connected with the positive polarity of your input voltage V1. So minus V1 divided by VT. Take this equation as equation number 1. Next we are going to write the IC2 equation. IC2 can be written as IC2 is connected with Q2. This emitter current is also IC5. So IC5 divided by 1 plus e to the power of minus of. So here this value is e to the power of minus of. This base Q2 of base is connected with the negative polarity of V1. So the input is minus V1 divided by Vt. So minus into minus will become as plus. So this equation can be written as 1 plus e to the power of V1 divided by Vt. That is taken as equation number 2. In the same way, we are going to write the equation for IC3, which is connected with Q3. This Q3 base is connected with negative polarity of your V1. So this Q3 carries the emitter current as IC6. So while writing IC3, this emitter current value is IC6. So IC6 divided by 1 plus e to the power of minus of, this base is connected with the negative polarity of V1. So minus V1 divided by Vt. So minus into minus will become as plus. Next IC4. IC4 is connected with the Q4. This emitter current is also IC6. This base is connected with positive polarity of V1. So we can write IC4 is equal to IC6 divided by 1 plus e to the power of minus V1 divided by Vt. Next, IC5 is the collector current of Q5. IC6 is the collector current of Q6. Now we are going to write a IC5. So IC5 depends upon the Q5. This base is connected with the positive polarity of V2. And this emitter current is IE. So we can write IC5 is equal to IE divided by 1 plus e to the power of minus of your input voltage is plus V2. So minus V2 divided by Vt. The same way, IC6 can be written as IC6 base is the Q6 base is negative polarity of V2. And the emitter current of Q6 is IEE. So we can write IC6 is equal to IEE divided by 1 plus e to the power of minus of this base is connected with the negative polarity of V2. So that is minus V2 divided by Vt. Minus into minus will become as plus. And we are going to substitute the equation number 5 and 6 in equation number 1, 2, 3 and 4. So this is your equation number 1. IC1 is equal to IC5 divided by 1 plus e to the power of minus V1 divided by Vt. We already know the IC5 value is IE divided by 1 plus e to the power of minus V2 divided by T. Just to substitute in this equation. So we'll get IC1 value as IE divided by 1 plus e to the power of minus V1 divided by Vt into 1 plus e to the power of minus V2 divided by Vt. Take this as equation number 7. The same way, IC2 can be written as, substitute IC5 in this equation. So we'll get IE divided by 1 plus e to the power of V1 divided by Vt into 1 plus e to the power of minus V2 divided by Vt. Take this as equation number 8. And also, we can write IC3 value as by substituting IC6, that is equation number 6 in equation number 3, we will get IC3 is equal to IE divided by 1 plus e to the power of V1 divided by Vt into 1 plus e to the power of V2 divided by Vt. Same way, IC4 also can substitute IC6 in this equation. We'll get IC4 is equal to IE divided by 1 plus e to the power of minus V1 by Vt into 1 plus e to the power of V2 divided by Vt. Take this as equation number 9 and 10. Now, we know that differential output current at del I. This is represented by del I. The difference between IL1 and IL2 is nothing but del I. So from this diagram, we can write IL value. So this is nothing but your IL value, which can be splitted into two ways. So IC1 and this current is nothing but your IC3. So the combination, that is addition of IC1 and IC3 is nothing but IL1. So we can write IL1 is equal to IC1 plus IC3. The same way, IC2 can be splitted into two ways. That is, this current is IC2 and this current is IC4. So the addition of IC4 and IC2 is nothing but IL2. So IL2 is equal to IC2 plus IC4. Now substitute this IL1 and IL2 in this equation. So IL1 is IC3 plus IC1 plus IC3 minus of IL2 is IC2 plus IC4. So now multiply inside IC1 plus IC3 minus IC2 plus into minus IC4. Now I am going to write this in this form: IC1 minus IC4 minus of IC2 minus IC3. Here I took the negative outside, that's why I am getting IC2 minus of IC3. Take this as equation number 11. We know the combination of IC1 minus IC4 values. IC1 is nothing but IE divided by 1 plus e to the power of V1 by Vt into 1 plus e to the power of minus V2 divided by Vt. Substitute in this equation minus IC4. IC4 is IE divided by 1 plus e to the power of minus V1 divided by Vt into 1 plus e to the power of V2 divided by Vt. Substitute in this equation. The same way IC3 also we are going to substitute in this equation. So IC2 value and IC3 value. So by simplifying this expression, we can write this del I value as IE divided by IE into tan h of V1 divided by 2 into Vt into tan h of V2 divided by 2 into Vt. So by simplifying this expression, we are getting this as the final result. Therefore, the change of the current can be, that is nothing but the product of the hyperbolic tangent of two inputs voltages of V1 and V2. The output voltage V0 can be obtained from del I by using. Next we will discuss about the analysis 2. In this analysis 2, we are going to consider the collector currents. See here, The transistor Q1 and Q2 collector currents are taken in the combination of IC5. IC5 is nothing but addition of IC1 and IC2. In the same way, IC6 can be the combination of IC3 and IC4. Like the same way in stage 3, IC5 and IC6 is the combination of IEE. So we can write it as IC1 plus IC2 is equal to IC5 and IC3 plus IC4 is equal to IC6. And in stage 3, we already saw IC5 and IC6 is equal to IEE. Let us assume the V1 and V2, that is modulation of V1 and V2, should be very much less than VT. So here we can write it as IC1 minus IC2 is equal to GM12 into V1. That is the difference between both the collector current. IC1 minus IC2 is nothing but GM1 into the corresponding input voltage is V1. We know the GM1 is the transconductance of your Q1 and Q2. Like the same way, IC3 and IC4, IC3 minus IC4 can be written as GM34, GM into V1. Here also the same input voltage V1. This is the GM34 is the transconductance of Q3 and Q4. We already know the general format of GM is nothing but emitter current divided by VT value. Here GM12 is nothing but a transistor Q1 and Q2 which is under the stage 1. So in stage 1, if you see, this value can be written as IC5 divided by VT because the emitter current of stage 1 is IC5. So IC5 divided by VT. The transconductance of Q3 and Q4 can be written as GM34 and its emitter, that is collector current, is nothing but emitter current of this stage Q3 and Q4 is the collector current of Q6. So the emitter current is nothing but IC6. So we can write it as IC6 divided by VT. So the differential output voltage V0 can be written as V0 is equal to RL into IC1 minus IC2 minus of IC3 minus IC4. We know already IC1 minus IC2 value is GM1 into V1. Just substitute in this equation and replace IC3 minus IC4 as GM into V1. So if you substitute in this equation, you'll get the equation as like this. Now in this expression, the V1 is common, so we can take it outside. So the remaining value is V0 is equal to RL into V1 into GM12 minus GM34. So here we already know the GM12 value is IC5 divided by VT and GM34 value is IC6 divided by VT. Just to substitute in this equation, so we'll get IC5 divided by VT minus IC6 divided by VT. This VT is common, so we can add it this value, that is IC5 minus IC6, the whole thing divided by VT. So V0 is equal to RL V1 divided by VT into IC5 minus I6. Take this as equation number 4. If you choose the RE value, this value will be very much greater than VT value. That is IC5 into RE combination should be very much greater when compared to VT. At the same time, IC6 RE should be very much greater than VT. Then we can write it as IC5 minus IC6. That is nothing but the collector current, that is at stage 3. The difference between these two collector currents IC5 and IC6 can be written as V2 divided by V2 is the potential difference in the stage 3 and the corresponding resistance is RE. So general format I is equal to V by R. So general format IC5 difference between these currents is equal to V2 divided by RE. That is nothing but corresponding resistance value. Substitute equation 5 in equation number 4. The IC5 minus IC6 is, we are going to replace the value as V2 divided by RE. So V0 can be written as RL V1 divided by VT into V2 divided by RE. So here rearrange this equation as V1 V2. Just I am going to take only V1 V2. Remaining values I am going to take as RL divided by VT into RE. So I am going to choose all these values as constant because the RL value is also constant value, VT is also constant, RE is also constant. So Overall this value I'm going to make this as k. So we can write V0 is equal to k into V1 into V2. So this is the final expression of your analysis 2. Next we will discuss about the applications of the Gilbert multiplier cell, which is used in most of the IC multipliers as the 4-quadrant cell, and also it used as a modulator or mixers in the communication circuits. It is used in signal processors also, and it used as a detector or demodulator to recover low frequency signals. And it is used as a phase detector, used as a frequency doubler, squarer, square rooter, and divider, etc. Thank you.